case 2 that we'll be considering is two different sets of data that ostensibly are measuring the same thing. We want to know if they agree. Some examples of this, maybe you have the same sample and it's measured by two different people. So you want to make sure that both people did the technique correctly and the results agree with each other. Another example of when you might want to use this is you have, say, the same sample but two different experiments, two different ways to measure it. Maybe you can do a titration or you can do a spectrophotometric measurement, and you want to make sure that those two different techniques agree with each other as well. So those are some examples of where you might want to do this sort of comparison. Now, in case 2, we don't have a value that we know is correct, and so it's not quite so straightforward. We can't just look at confidence intervals and see if they overlap or whatever. So we have two different tests that we have to perform to know which exact way we're going to do this. The ultimate goal here is we're going to do what's called a t-test, and this uses students t to see if we have agreement. But there are two different ways of doing the t-test, two different formulas that we can use, and to answer the question of which formula we need to use, we first need to do what's known as an f-test. Now, the idea behind the f-test is it's a way to compare standard deviations. When we have our two different sets of data, the question that matters here is, are the standard deviations relatively close to each other? Are they basically, statistically, could we say that all this data comes from the same set of data that has the same standard deviation? So if we have, say, if we represent our data with a Gaussian curve, are the two Gaussian curves mostly the same shape, or is one much narrower than the other? And the way we do our comparison will depend on whether this is true or not. So the f-test tells us, are these standard deviations statistically the same or similar enough that we can assume that they come from the same pool of data, or are they so different that we have to do a different test? So the way to do this is we have a statistical test parameter that we're calculating called f, and the f calculated is equal to s1 squared divided by s2 squared. So this one isn't difficult to calculate. And the convention is that we choose, for our two sets of data, choose s1 to be the larger standard deviation, so that you always get a number bigger than 1. Okay, so and then we compare this to a f table. Similar to our students t table, we have a table of f values that will depend on different degrees of freedom. Okay, so if f calculated is greater than f table, then we reject the null hypothesis and we say that the standard deviations are statistically different. And of course the opposite, if f calc is less than f table, then we stay the same. So the f calc being greater than f table would be this. F calc being less than f table would be this case here, where we can basically treat the standard deviations as being the same.